our first seminar of the new semester. So, as I'm sure you've all realized, our speaker today is Leen Decin from KU Leuven in Belgium. So Leen's an expert on evolved stars, instrumentation, infrared calibration, and also exoplanets. So Leen did her PhD at Leuven, followed by a few postdoctoral fellowships around Belgium and Amsterdam before returning to Leuven, where she's now a professor and is coming towards the end of a ERC consolidator grant. So today she's going to be talking to us about the ALMA ATOMIUM Large Program, which is substellar companions shape the winds of evolved stars. So Leen, thank you very much for agreeing to come speak to us, and please, whenever you're ready.
Okay, thanks Ed for the introduction. So indeed, I will try to explain you today some of the results we have obtained with one of the ALMA Large programs. It is called ATOMIUM. And so for today's discussion, since you might have quite different backgrounds, I will start with a short introduction before jumping towards one of the latest results that we have obtained. So can you see my mouse, Ed, if I can ask you?
Yeah, I can see your mouse.
Yeah, okay, thanks. So if we are now talking about the chemical evolution of the universe, the mass spectrum of white dwarfs and planetary nebulae or black holes, the frequency distribution of the supernova, or the fate of exoplanets, one of the key aspects we always need to understand is how much mass stars lose throughout their lifetime. And so the talk of today, as you could see already on the title, is that I will focus on cool aging stars. So these are these asymptotic giant branch stars and the red supergiant stars that are stars with, let's say, an initial mass above 0.8 solar masses that are really at the end of the lifetime. And during that phase, they lose a lot of mass through a stellar wind. Now, these stellar winds have for a long time been depicted in the way you can see it here. You know, the first luminous stars have already been detected by Miss Maury in 1897. And then it was Hertzsprung who have classified them as being these red giant stars. And then in 1956, the first indications have been seen that these red giant stars do have stellar winds. And so the morphology of these stellar winds was thought to be spherically symmetric. And this makes their analysis, if it comes then into the numerical coding, much more easy than having to realize or having to deal with three-dimensional structures. So that makes them some peculiar objects almost, since most all other dynamics and thermodynamics that we are dealing with in astrophysics is often already described in much more complex way. But these stellar winds and also these stars, they're also very interesting from another point of view, since in the stellar winds, you can see that a lot of molecules are created. And at some point where the densities are high enough and temperatures low enough, these molecules can condensate. You can see it here, it is a dust formation region. And that's extremely important since dust grains do have a much larger opacity and also geometrical extent. And so the interaction with the photons of the star have as a result that the stellar winds can be triggered. So if no dust grains are formed, no stellar winds will be there. And so these AGB stars, given the fact that they are quite easy in terms of, are thought to be easy in terms of geometry, but quite intriguing in terms of chemistry, they are somehow ideal extraterrestrial laboratories. What I mean with that sentence is that if we can, for instance, use these targets to unravel chemistry and to understand, for instance, what are important channels to make some molecules, we can use that same knowledge, for instance, if we're speaking about exoplanets, if we're speaking about planet-forming disks, and so on. So they can be used as a kind of a benchmark to unravel the chemistry ongoing in the universe. And so with this schematic, I summarize a little bit the things I have been saying already, and I add some more concepts. So this is roughly a schematic of how can the stellar wind around an AGB look like. You can see again in a 1D perspective. So you have the nucleosynthesis in the star itself, and there are convections and redshifts. And then the star is not static, it is pulsating, and actually we do not yet understand fully the pulsation mechanism, but the fact that you have pulsations, and you can see it here at the bottom part, implies also that you can have shocks. And owing to these shocks, the gas phase chemistry can be really out of equilibrium. And then in the next phase, and this is what I've explained you already, these molecules and then the fraction of atoms still there can form the dust species, which are the trigger for a stellar wind to be launched. And then you have the outer wind region, where UV photons from the interstellar medium, they can penetrate, they cause photodissociation, and also a whole bunch of other gas phase and gas dust reactions occur. Yeah? And so, as I've told you already, what is so important in terms of our general knowledge of astrophysics in its very broad context is understanding what is happening here. And then with the main idea, or the main goal is trying to understand what are now these mass loss rates, if I'm aiming to connect that to, for instance, the enrichment of the universe, to the fate of other stars, and so on. Yeah? So, as you all know, there are roughly two methods to understand or to say something upon mass loss rates for this kind of stars. Eh? You have the forward methods and retrieval methods. The forward methods are the classical theoretical predictions, and you try to do that as fully consistent as possible. And the retrieval methods, for that you rely on observations. Often you cannot compare these observations with completely, let's say, with these forward models, since this first class is too CPU intensive to do all calculations for a comparison with the observations. But I can add a point to that later on, since we have another idea, but that's a detail now. But what is currently, let's say, the state of the art? The state of the art for these forward models is, okay, you do that as consistent as possible. You include the things you know upon the gas dynamics, the dust dynamics, the radiative transfer. You need to model, okay, if I form some molecules, what is then the impact on the heating and the cooling mechanisms? If the temperature is changing, can I then form some dust grains? Are densities still large enough? What is the interaction with the stellar radiation field, and so on? Now, that's for everybody who has done this kind of a numerical code, the fact that you do not only need to understand the dynamics, the physics, but also the microphysics, with which I mean chemistry, radiative transfer, implies that this kind of models are very CPU intensive. But a lot of groups in the world have done their best to try that as good as possible. And I give you here one example, and it was an example that is not yet accounting here for this time-dependent behavior of the pulsations, but was doing a very good job in all of the other fields, which are still colored here in this picture to the left. Yeah? And so this kind of a model, what you can see is given then your input parameters, and I show that in a quite abstract way here at the top, the mass, the temperature of the star, the luminosity, and the chemical abundances. Then you use your model with all its beauty, and you predict the mass loss rate. And so then these are the input parameters. For that model, you had a particular prediction of 8 times 10 to the minus 5 solar masses per year. That's one point. But another point you can see here as well on this picture. This is if you now look, for instance, to the velocity, that looks quite fine as being that you can describe that with the power law. The same holds, for instance, for the gas temperature. So what you can do and what is done is using this kind of forward models to inform your retrieval and to say, okay, these models tell me that I can use power law approximations for instance, the velocity field, for instance, the gas temperature. And so again, various groups in the world have then used that kind of a knowledge to analyze observations. Now, stellar winds can be analyzed or depicted in various ways. I just show you some examples. For instance, you can look to carbon monoxide. Carbon monoxide is next to molecular hydrogen, the most abundant molecule in this stellar winds. And it's also very stable. I mean, stable, I mean, it's not very much reactive with other molecules, and it's also not very reactive in terms of dust condensation. So it's quite simple. You can also look, for instance, to the signature of the dust in your SED, your spectral energy distribution, and you can use that. For instance, here you can see these little bumps. These little bumps here in these spectra, they come from silicates. And so you can use that kind of information to also say something from observations. What are now these mass loss rates? What do the observations tell us? And if you can do large sample analysis, and that mainly holds for SED analysis, which are much more simple and much more fast in terms of their analysis, you can also give relations. You can deduce relations for the mass loss rate in function of the luminosity and the temperature, for instance. I give you two of them here. But, and now comes a very important slide. Given all that we have done in the past, this is currently the outcome of our knowledge of the mass loss rate in function of some parameters. So what you can see here is the mass loss rate at the y-axis and function of the luminosity for a star of initial mass, two solar masses, and here for a star with effective temperature constant at 2800 K. And you can see here different mass loss rate prescriptions. Some are shown in full line, some in dashed line, and another one dot dashed line. The dashed lines are the ones which are the forward models. The full lines, they come from the retrieval approach, and the dot dashed lines are somewhere in between these two. If your winds, if the timescales that come from the wind mass loss rate are shorter than from the hydrogen burning rate, then you are in a wind-dominated regime and vice versa. So that are the two colors, the blue and the orange color. But whatever I'm telling you, you can see here immediately without knowing how each of these persons have deduced the mass loss rate is the huge difference we see between each of them, between retrieval approaches, between theoretical approaches, and so on. This is not only the case for the AGB stars, the same holds for the red supergiant stars. And by the way, for the red supergiant stars, it is only in 2020 that one of our postdocs here, Leen Decin, has deduced for the first time a theoretical prescription for a mass loss rate for red supergiants based on turbulent pressure. But also here, the same message holds. Can I tell you something upon a mass loss rate in function of one of the key parameters of a star? No, I can't. But if I can't tell you that, and given also here this blue and this orange color, so implying that whenever you have in the blue regime, your wind is dominating the stellar evolution, you will also immediately understand that there is a huge issue with our prediction of stellar evolutionary tracks. And this is shown here in this slide, where for various of these mass loss rates, I have here shown some evolutionary tracks. So you have an initial mass, so between 0.8 roughly and 3 solar masses. And then we just follow what is this mass doing in function of the luminosity as the star is evolving along the AGB phase. But depending on which mass loss rate prescription I am using, you can see that the behavior of the stellar evolution track is extremely different one with respect to the other. And so just for people looking to all the little symbols here on the slides, I just have shown here with the colors, what happens if, for instance, the green color here indicates that the mass loss rate starts to be above 10 to the minus 8 solar masses per year. Orange, yellow, 10 to the minus 7 solar masses per year. And the red circle, it means that here the winds start to be dominating above the hydrogen burning. But main message here is there is a huge issue. We do not understand or we cannot predict mass loss rate, and as such, everything we are aiming to tell you upon evolutionary tracks, how will stars end at the end of the life, what is the mass, what is the connection of lifetime between from the main sequence up to the white dwarf, it's very much uncertain. So there are various issues underlying the relations I have shown you on, and I will for sure focus on only one today. And the one that I will focus on is on the fact that this geometry that we have been thinking was valid, this one-dimensional framework, seems to be very problematic. And it's very problematic for various reasons, and the reasons are shown here. We see multidimensional things happening on various angular or various geometrical scales. We need, and we already know that for our models, we need to account for the fact that these molecules that form then larger gas phase clusters, that these gas phase clusters that finally end up in the dust grains, we cannot make a rough approximation from saying, whoa, everything here is nicely spherically symmetric. We need to account for the fact that these larger gas phase clusters have a very complex geometry, and we need to understand and calculate, for instance, their potential energy surfaces. On a larger scale of 1 AU roughly, we need to account for the fact that the pulsations and the convections of these stars induce a complex pattern at the surface, and that we can see this pattern also in the observations. So the bottom one is an observation. This is a prediction, and this is as well a prediction. But for today, I will focus on a larger scale, even scales between, let's say, 5 and 500 astronomical units, where you can see from observations, the upper and the middle one, and also from models that I cannot claim at all that these stellar winds are spherically symmetric. And so if I'm aiming to say something upon each of these aspects, so the first slide of today, then I need to understand how this mass loss rate, how that can differ if I now use proper knowledge on the 3D structure, and also if I account for how that changes in function of time. And so this brings me then to the main topic of today's discussion. What do we see here? What has ATOMIUM, so that large program, that ALMA large program, what does it tell us about the origin of these structures here? And you can see it already here on the title. It is the impact of a companion, a planetary companion or a stellar mass companion. And so now I go back in history and I show you here some pictures I've taken, and I was quite lucky since I have the book here in my office. And so this is the first photographic atlas of planetary nebulae. And planetary nebulae are the stages just after the AGB phase. And so Curtis, when he was looking at his new photographic plates, he already, you can see it yourself, he clearly distinguished various morphologies. And so at that age, it was even not yet understood that this planetary nebulae are the successors of the AGB stars. But already in that publication of 1918, you can see that sentence of Curtis. So he was wondering if it would be possible to postulate any general form or forms which shall be mechanically plausible, and to which the planetaries or considerable proportion of the planetaries will more or less closely conform. And so that question has been open for more than a century, and let's say we think we have solved it now. Since this is the issue that we will address today, how can you understand that picture? So a picture taken by the Hubble Space Telescope. And so also other data that were saying, okay, these AGB stars, They are roughly spherically symmetric, so 80% of them. But then if we look to their successors, to the PNs, the planetary nebulae, we see that, yeah, depending on which study you look at, less than 20%, or sometimes even only 4% of the successors do have a spherical geometry. So how can we understand this transition? So various causes have been proposed in the past. So what could be the causes? So it might be that the impact of stellar rotation can give you kind of a bipolar structure, or potentially magnetic fields. But yeah, these AGB stars, magnetic fields have been detected now, but they are absolutely not very strong. So that's a bit questions. Or it might be kind of a snow plug mechanism, since these AGB stars, they have quite a slow wind, roughly 15-20 kilometers per second. But when the star starts to become a planetary nebula, which is much more luminous, and go off of much more, and then also turns back in the HR diagram, you start to have another type of stellar winds, much more line-driven stellar winds, which has a much higher speed. So this higher speed winds can collide with the slow speed winds, so the remnants of the AGB, and that potentially could also give you some instabilities or potentially some very peculiar morphologies. The mechanism that was most supported, let's say the last 10 years, maybe even 20 years, is the one that is invoking binarity. But it's a very peculiar kind of binarity. It is binarity of two companions that are so close to each other. So in the lower part, you can see that they form a common, that they form a common envelope. So it's called common envelope phase. And so typically they have orbital periods lower than 10 days. And this is now where atomium comes into the picture. So this movie is made by one of the journalists when we were presenting our results. And so what have we been seen by using ALMA? So ATOMIUM is, as I've said already, it's a large program, ALMA large program, roughly 113 hours, where we have taken the instruments at 3 different arrays, so that we have different angular resolutions of the stars. And we had a sample of stars that have been observed in exactly the same way. And we have taken a very specific band 6 for ALMA it is, of which we knew that there are many molecules there as well, since we were not only interested in understanding geometries and so on, but this large program has a lot of points that we wish to address. So also the dust formation pathways, for instance, and the gas phase chemistry and so on. So the results I show you today is only a very small piece of this whole data we have. So we have bought special servers, we have terabytes of data, and I will only focus with you today on 2 spectral lines of what we call the mid-angular resolution data, while we have 200 spectral lines, while we have three different angular resolutions. So it's only a very small piece. And so this is what we have been presenting in the science paper that was published in September 2020. And so what you can see here is what we call the gallery of the winds of red giant stars. And you can see immediately, and I show you again the picture I've shown you already of this planetary nebulae, that there are, in terms of morphology, quite a lot of similarities. So the fact just from looking to, for instance, what do I mean with similarities? You see here these bipolar outflows. Okay, we can see that also here. You can see it here in this one as well. If you would focus not on the one that I have here, but some of them have clearly arc-like structures. Here you see broken arc-like structures. You have even not nice spiral-like structures. This is one we call the rose. The fact that these geometries look so similar, as I said already gives you one or two conclusions. It is the same physics that shapes both AGB winds and PN. And by looking to the AGB winds, the predecessors of the PN, we have got the mechanism in act. Since for all the mechanisms, you remember these four blue mechanisms I have shown you already, or they were shown in blue. Each of them was acting on the star itself. And each of them, you know, if people were thinking about stellar rotation or common envelope phase, they had to invoke the mechanisms at the extreme end of the AGB. So just before turning into planetary nebulae. And here we say this is not true. The mechanisms that is acting is not only acting at the extreme end of the AGB or even not only during the PN phase, it is acting already much earlier on the AGB track. So how have we diagnosed then, or how have we tried to find the mechanism that is important? For I do not know if people in the audience have worked already with ALMA data. I just show you what we now call as our decision tree. Since you should realize you have all this data on your hard disks, and it starts to be extremely challenging to find your diagnostics if you have so many things. And so what we found finally by working a lot with the data is that following this kind of a tree was very important for us. So we first looked to the carbon monoxide channel maps, and we used to say something already there on morphologies. We say, okay, we could say some of them are spiral-like, or broken spirals. Some of them are much more bipolar. So that's a first marker that you take. Then you look to the kinematics. Since I've told you already, you know, these stellar winds are triggered by the formation of dust grain. And given the knowledge that you have them, we know that the stellar winds is lower close to the star, is arising then quite fastly owing to dust formation, and then you reach the terminal wind velocity, so the upper graph here in the middle panel. But for quite a few stars, we did retrieve another kinematical picture. So not at all compliant with the idea we had in our mind upon the radial structure of the velocity fields. And then we look to the what we call moment one maps and PV diagrams. Moment one maps gives you an idea on the velocity structure. And you can see here very clearly for that star, the difference between blue and red. Blue is material coming towards you, red is material going away for you. So this can be an indication of, for instance, a bipolar structure, or for instance, Keplerian rotation in, for instance, and kind of an equatorial disk. So we have used that kind of knowledge, and we were gathering that in a kind of a huge Excel sheets. And that started to be so complex, you know, you start with crosses and marks and so on. But I still remember the day that I was a little bit fed up with looking to all my notations, and that I just thought, okay, I will use colors, since colors are maybe easier to understand something. And now I will color what you see here, since I haven't told you too much yet about what you see here. But if you're grouping colors, then you can see this. Your eye immediately can see that there is a classification here. Class 1 are the ones where we could see what I will later explain you as an equatorial density enhancement, where there might be even indications of Keplerian rotation fields. Type of class 2 are the ones where we see bipolar structures, both in the morphology as in the dynamics. Class 3 are dominated by spiral-like structures. Now, this classification is not a random one, since the stars are not random here in my sheets. You could see that coloring if I'm ordering the stars in function of their mass loss rate. You can see here that the mass loss rate is increasing from the upper to the lower part of this table. So this implies that whatever mechanisms I'm looking at, for some reason, it has a correlation with the mass loss rate, and we could quantify that with the Kendall-Tobie correlation coefficient as with a number of 0.79, which is really high. So of all of these mechanisms that I have proposed you, which one of these shows a correlation with the mass loss rate? Well, there is only one. Since the other three, I really would need to fiddle around with the models to have that kind of a dependency. The only one that has almost a spontaneous or natural correlation with the binarity, with the mass loss rate is binarity. But it's not binarity that is only restricted to the common envelope phase. I will show you that it is binarity in a much broader context, also including long period systems with orbital periods above 1 year, so with orbital separations above 2 astronomical units. So we come to the lectures of binarity that you have had, I hope, once in your life. So we are concerned about the Roche Lobes. Where are they and what can be the impact of one star on something that is happening close to the other star, in particular when they are close to the equipotentials. So there are roughly 3, and you will see I have a blank one, so there will be 4 main categories here. I have already introduced to you the common envelope phase. The 2 stars are so close to each other that they have a common envelope. There's also the phase, the semi-detached phase, where one star is filling its Roche lobe and via L1 material is transported towards the other star. And then you have the detached phase where the Bondi-Hall-Littleton accretion is acting. And roughly and now I'm thinking, it's roughly some 20 years ago that another class has been introduced. It is a class, no, it's not 20 years, it's 10 years ago, sorry. It is a class where it is not the star that is filling its Roche lobe, it is the wind that is filling the Roche lobe. And it is with wind material that can be tunneled, I would say via L1, but if you really look into the simulations, it's just next to L1, but material is tunneled towards potentially the companion star and might eventually form an accretion disk there and also other kinds of morphologies. This class is a very important one for the story of today. So how can now, given now that knowledge, now you should wonder how can a companion then change the stellar wind of an AGB star? I try to explain that to you and I try to gradually add some complexities. So one of the first people working on that field in terms of also numerical simulations was Mastrodemos et al. In 1999. And here you can see a detached binary system, period above 1 year. And yeah, you cannot see it here, but there is a companion somewhere there. And you can see that that companion, you can see the stellar wind, phase on to the left, edge on to the right. And you can see in the phase on picture, you see this very nice delineated almost spiral that you have. It's a spiral shock that you get here. And that spiral shock can be quite easily understood. It's mainly the effect of the AGB star that is wobbling around the center of mass of the system. And you can understand that if you wobble around your center of mass, meanwhile you lose some material, that this will impact your wind morphology and that can create this kind of a spiral you do see here. If we then look at the spiral edge on, you can see that the spiral structures almost reach up to the orbital axis. So they are very wide arcs. So depending then on the inclination of the system, you might see either, for instance, a spiral, or you might see arcs, quite regularly spaced arcs. You can also have other systems, depending then again on what is the mass of your companion, what is the orbital separation of your companion. So here you can see a second example. Again, you see kind of a spiral structure, but this time the spiral you can see is attached to the companion. So it is, in this case, it was mainly a spiral that comes from the Bondi-Hall-Littleton accretion. So let's say it's mainly the gravitational interaction with your companion. it impacts the gravitational potential, and as such, material is attracted towards your companion, and the companion can steer it around. Meanwhile, also you have the normal pressure that's acting, and so that spiral that is created is slowly going outwards in terms of radial distance. If you now look edge on, you see that you don't have anymore the signature that reaches almost up to the orbital axis. You see much more confinement towards the orbital plane. And this is what we now, let's say, generally call an equatorial density enhancement. Some people like to call that a disk or a torus. I will not do that, since this automatically, for me, implies more knowledge upon the velocity vector field, which we not always have yet. So in general, we call that an EDE, so equatorial density enhancement. This is 99, and meanwhile, quite a few observations have already been showing, so even before our atomium data, that indeed these AGB winds do show all kinds of morphologies. There were already spirals detected. They're also much more complex structures, so you can see here kind of a herd-like system. Here you can see, it's much better depicted here. So for people working with ALMA data, the red and the blue signature, this was here interpreted in terms of a Keplerian disk, so disk or an EDE with a Keplerian rotation field. Yeah. This kind of observations have triggered also, as of 2012, let's say a new boost in our field for the numerical models. Yeah. So with various groups, we're now trying to model these storms. And you can see here various people, only a restricted list, each of them with a particular focus upon how will we model that. But know that since these models are so CPU intensive, most of these publications only deal with 2 systems, 10 systems. So it has only been lately, and lately I mean 2020, that we start to become in the phase that, given some model with its assumptions, we can, for instance, model 70 systems. But even 70 is still quite restricted if you have quite a large parameter space to be sampled. Yeah? I will show you one of the latest results. And why do I prefer that one? Since most of the simulations are still in the realm of showing you densities. What is it? How does the companion impact the density in the wind? But this is not what we see as astronomers. As astronomers, we see the lights. So we should not only be interested in the densities, we need to do proper chemical calculations, so non-equilibrium chemical calculations with the network. So it slows down the computations enormously with the factor 50 roughly. And on top of that, we need to have very efficient 3D radiator transfer tools to also, get the radiation, so deduce the light that we can see in our from these targets. Yeah. And so what we did, the code, the radiator transfer code that we are now using is a code that is a Marguerite code. So for people interested in that, it's a new, very new solver that has been developed by one of my PhD students. And it will become publicly available very soon. It does outperform all other existing 3D radiator transfer codes in terms of efficiency, in terms of accuracy. And there's also a new module that should be ready in a few months that will also directly give you information on your uncertainty predictions. So what I will show you now is a movie. Before showing you that, I will tell you what will happen. Yeah? You will first see how, for that particular simulation, you will see the density, the CO over H2, and the temperature. You will see that you will see it's changing in function of time. Once we went through the simulation, we will turn the simulation around so that you can see it for various inclination angles. And then I will show you the predicted light as you could see it with ALMA. And you will see it as we travel through the line profile, so for the red shifted and the blue shifted information. So this is now, Yeah, so the simulation has started. You can see how the companion impacts the structure of the wind, and the AGB star is pulsating. This is what you see here, the first ripples there. Now the system is inclined, and you can see here we roughly reach 90 degrees. Now we show you for 90 degrees, 45 degrees, and then 0 degrees, first at 0 speeds, and now we travel through the line, how channel maps in general do change if you look at your spectral line for various velocities offset with respect to your rest velocity. Yeah? And so it's for the first time that we now have this kind of, let's say, information in terms of molecular line radiation that we can use to confront with our observations. Yeah? And so it's a whole new field in terms for the numerical simulations as well that is now opening, since aiming for understanding these AGB winds implies that we need to have a lot of effort in doing these numerical models properly. Yeah? But I can tell you a little bit more already, since although we are now so hardly focusing on these numerical methods, we can tell you already some more things. Eh? So this is what I've told you. It is binarity. I see correlation with mass loss rate. But then you can have two concerns. Where does the correlation with mass loss rate come from? And you can't see the companion here. So where is that companion, since these red giant stars are really very, very bright? Eh? So how to probe the invisible if you can't see it? Well, then statistics can give you some hints. Eh? So let's look at this table. We now look not to the AGB stars, but to the main sequence stars. So stars that finally might come AGB stars, and if they are more massive, red supergiant stars. I make a differentiation here between stars with spectral type FGK, initial mass between 0.8 and 1.5 solar masses, and A and B spectral types, 1.5 between 1.5 and 8 solar masses. And you can see here a summary of what people have published for the population statistics, how many stellar companions and broad dwarfs has one found. What about planets? Planets close by, between 2 and 10 AUs, planets further out. Yeah? Given the statistics, it's already very clear, especially in the first and the second column, that the more massive you are, and that's also natural, the more companions that you can have. Then you should account for the fact that some of these companions will be driven outwards or will spiral in, owing to tidal interactions, when a star is evolving from the main sequence up to the AGB star. So roughly we estimate that we will lose some 10 to 20% of these companions during the AGB evolution. First point. Second point is that one. And it is a point that we only have realized, I would not say too late, it was almost when publishing the science paper, since we were a little bit struggling yet. And this is that part, is that I have been showing you these mass loss rate diagrams. You still remember? They all had a minimum mass above 10 to the minus 7 solar masses per year. But if you now look to stellar evolution calculations, and if we think, for instance, of our own sun with a mass of 1 solar mass, our own sun will only have an extremely short period in its life where its mass loss rate is thought to be above 10 to the minus 7 solar masses per year. And why do I say that? Well, for these observations to have some signal to noise, and not only for the ALMA data, but also for lot of other diagnostics, we are roughly restricted to that limit. But given that limit, it also induces a bias in our initial masses. That limit, and given our knowledge on stellar evolution, implies a bias that the stars to which we are looking are stars with an initial mass above 1.5 solar masses. But this brings us to the lower part of this upper table, that stars with an initial mass above 1.5 solar mass have indeed on average more than one companion. So this is a way to be confident that indeed companions are important for the majority of AGB stars with a mass loss rate above that limit, including also the ones in our atomium sample. And then that correlation with the mass loss rate. Yeah? So what I will show you here are some first analytical predictions that we have done, since we didn't have yet we didn't have yet a large sample of numerical simulations that could show us that correlation. Yeah? But if you don't have that yet, you can always simplify the case and try to understand if you can see that correlation just taking some analytical considerations. Yeah? And so you see here, it's a factor that we have defined. And for the interested people, I would say, let's have a look at the science paper where we describe it in more detail. So that factor, it's a dimensionless factor, and where we introduce p-wind and p-comp. And so p-wind is the radial momentum of the wind material that the companion encounters in one orbit, and p-comp is the tangential momentum of the companion. And if you then look to some extreme parameter, or let's say extreme corners in your parameter space, you can calculate that. And what do you see here? You see, well, I have rescaled it here, which is not important, but you see here that this Q factor, as we show it here, is inversely dependent with the mass loss rate, is also inversely dependent with the orbital separation. So it implies that, and that's natural, the shorter you are to the star, but also here, the lower the mass loss rate, the more impact you might have. I mean, the more different your geometry will be from a spherical symmetry. I mean also that your, how should I say, that your velocity vector field is not radial anymore, but you see these tangential components that imply that, for instance, part of the material that is lifted off of the AGB star is, for instance, falling back towards that equatorial density enhancement, potentially also forming Keplerian kind disks. Yeah? Okay, we are almost there. Since then you say, okay, that's fine. We hopefully you believe me. But if you know this, can you do some predictions? Right? Can you say something upon what is the change of the orbital separation along the AGB star? Right? And so we have done this calculation. I show you one example. It is for the primary with a mass of 1.5 solar masses. And then the 3 different colors are for different masses of the companion. And so you see 4 panels. We start with an orbital separation of 2 AU, 4 AU, 10 AU, 25 AU. And you see that along the AGB, how the orbital separation is changing. You see that, for instance, Jupiter-sized planets, they all widen their orbit. While, for instance, here, the golden color shows you that that companion, a stellar companion, is spiraling in when the AGB, when the star, the main primary, is evolving along the AGB. Hence, can we say something more? Well, if we now look to the population statistic, you know the table that I've shown you, I think 2 slides ago. What do the people claim that have studied the orbital separations of stars, of planets around main sequence stars? Well, analyzing this population statistics, it seems that most, I don't say all, I say most, majority of them have an orbital separation above 20 astronomical units. It implies that we are in this regime, that for most, again, of the companions, we should see a widening of the spiral through evolution of the primary on the AGB. And so this gives us a way of predicting, of giving you a scenario for the AGB morphologies. So what do we think is happening? That through time, most of the stars with the low mass loss rates do have an equatorial density enhancement or a disk. There's always a little bit of a spiral, but the dominant feature that we would see in our data is the disk. And through time, the orbit widens. It's also like that on the AGB through time, the mass loss rate increases. That then we come into the bipolar regime and we end up with a phase that is mainly dominated by a spiral-like structure. So this scenario that we are now predicting is something that we are aiming to test with a lot of other observations, but currently the test that we have done, the scenario is still valid, but I'm open for other scenarios, let's say like that. It also, our calculations very clearly show you that if you aim for detection of exoplanets around evolved stars, you should look for the first phase. So when these AGB stars still have a very low mass loss rate. Now that understanding, given the fact that we have here this scenario, we suddenly could also understand a lot of other results that were published in the literature, but that were, let's say, almost lonely results without having an overarching framework to understand that. Yeah? And so we could say something upon detached shells, upon PN morphologies, upon, for instance, the fact that you should know that for this planetary nebulae, the successors, they only have disks when they are oxygen rich. Yeah? All of that we certainly can explain. There are still some details that I'm skipping here, since this will be too much of a detail, I think, for the audience I have here. But if you want, you can always read that in one of the publications. Yeah? But now I'm almost done. There's an implication I wanted to discuss with you, and I want to come back to the start of my presentation, these mass loss rates. Yeah? We have seen this simulation, and if you do these simulations, we have a consistent prediction of the mass loss rates. Given the fact that there is here a companion, that companion impacts the mass loss rate owing to its gravitational potential. It just change it, so it can lower and it can induce an increase also in the mass loss rates. So if I would now do the same simulation without the companion, you can see that the mass loss rate is a factor of 6, 6 lower compared to having a companion here at this distance. But all of our analysis until now have been done under the assumption that there were no companions. Given that fact, it implies that our mass loss rates that we have been deriving can be horribly wrong, since we never have accounted for the fact that a companion is inducing a change in the mass loss rate. And it implies that for single star evolution models, which have always been thought of being, okay, they are single stars, and this is also the mass loss rate prescriptions that are inherent in stellar evolution codes, such as MESA, they do overestimate the mass loss rate in their codes. But if your mass loss rates are overestimated, this has an enormous impact on various things. And I show you here a very complex slides. Yes, there is less mass loss, there might be more nuclear fusion, you might have a brighter AGB tip, and I can continue. I will not do that. I will end here, but only I will end with one more slide. What does that knowledge implies also for exoplanets? Since, as you could hear in the introduction, that's also one of the fields to which I'm more and more focusing, mainly towards the climate simulations for these exoplanets. Well, I just give you here an example of which might potentially be an academic question. Yeah? You have here the Earth, Mars, and you have our Sun. Yeah? You should know, I hope, that when the Sun starts to be a red giant, and luckily our Earth will be engulfed. But no, let's take it broader and let's go to the exoplanets. If stars have a lower mass loss rate, compared to what we thought would happen, this implies that more stars will be engulfed by their by their sun, owing to the fact that tidal interactions will be much more severe, and that given the fact that then the primary will be more massive, you will have stronger interaction, and your planet will in spiral. And with this, I would like to end, and I would also like to end with an explicit thanks towards my colleagues who have helped me a lot with this presentation also, but also in getting these nice results. Thank you. Should I go out of the presentation now? Is that easier for you, Ed?
No, maybe keep it up in case the people have questions. So Leen, thank you very much. It was a really, really nice talk, really far-ranging in terms of the sort of the topic and the impact of what it has, all the way to exoplanets, which was nice to see. So I imagine there'll be quite a few questions. So I can see Tom's got his hand up. So maybe Tom, want to go first?
Yeah, thanks for a really nice talk. Some absolutely beautiful observations, and also the models look amazing. I'm really looking forward to hearing about how you've done that. But yeah, my question here is maybe a bit of a nastier one, which is you had that huge spread in the 1D models in the massless rates, and now you're showing that the 3D model massless rates are different. Do you have confidence that if a whole bunch of people do 3D models that you're going to not see a similar spread in the outcomes?
No. And for the very simple reason that this 3D hydro model, as you know it, there's so much complexity that one needs to include that it will still take us a lot of time before we have fully consistent, the fully consistent picture. The main issue, as you might understand, Tom, there is that, and that's independent of 3D versus 1D, is the fact that we do not have a firm understanding of the dust nucleation process. So we have here people working on the predictions of these larger gas phase clusters, but it's still such a long way to go there in terms of chemical understanding before we can put that in a fully consistent way in this kind of simulations. So we have that now in a more simplified way, but yeah, already given that answer, my answer to your question is no. I think potentially what might be best is going back to our observations, and trying to better quantify how much we can have been wrong, given the fact that we have interpreted this data as being single stars while they are binaries. And since everybody, if we look into the literature, each of them claims we have an uncertainty of a factor of 3, and the brave ones say a factor of 5. But that's not true. There is a systematic issue there. And so that's one of the goals of one of my PhDs. He is trying to quantify that systematic problem. But she just has started her PhD, so maybe 3-4 years, and then I hope to have a better answer to that.
Great. Thank you.
Cool. Simon?
Oh, yes, well, yeah, thanks a lot for a very interesting talk. So I have a question about one of the 4 mechanisms you outlined at the beginning in the blue shapes. Yeah. So the snowplow mechanism, so where the slower AGB wind gets overtaken by fast wind, and that can now if the whole setup is completely spherically symmetric, then it would never give you an asymmetric planetary nebula, right? So in that mechanism, what was supposed to give the asymmetry in these planetary nebula?
That's a very good remark, since some people say that it could give them asymmetries, but that can only happen if you have some instabilities that can grow. But even an instability, in my opinion, is not something that can give you this very prolonged, let's say, for instance, this bipolar outflow. So then there have been suggestions of combining these two. You have stellar rotation, and as such, you might have some elongation in the wind and the star, and that the both of them combined could give you this kind of a bipolar structure. And why not combine it then with some particular magnetic field? So people have been trying to combine then the 3 mechanisms in order to get some predictions.
Okay, good, thanks.
Okay, does anyone else have a question? Right, Tom, one more.
Yeah, sorry, if no one else is going to ask one, I will. So this is a bit speculative. Do you have enough data to measure spectral indices in these AGB winds, or is that something you're planning to do? Is it only band 6 data that you have?
We have only band 6 data, but quite some of these targets have already been observed at other frequencies. So we can do that. And this is something that currently Anita, one of the ATOMIUM members, is working on. So why are you asking?
Well, just to learn about the nature of the dust in these winds and if that helps to constrain these models as well.
Yeah, but so we have quite well, for quite a few of these targets, we have already quite an understanding just from the SEDs, and sometimes we have data that does show us the dust in function of the radial distance. So we have interferometric data. So most of these stars either have aluminum oxide bands or silicate bands. So we do know that roughly, yes. But that does not, it's always, you know, that there's a huge degeneracy in saying something upon the composition, but also the radius of the grains and then the aspherity of the grains itself.
Thank you.
Leen, I had a question as well. So with, you're mentioning, I think you made a very nice case for binarity as being sort of probably the dominant mechanism for the structures that we're seeing, and you touched upon that the companion star would move as long as it started about 20 AU or so away. It would move further out during the AGB phase. Do we have good enough statistics of the sort of the separations in binary stars for the A and B stars prior to the AGB phase to put kind of constraints on that? And then can you predict forward with your models what fraction of AGB wind structures should be spiral versus EDE? And
you can do that, and this is what we have done in the paper as well. So if you take the compilation of data that has been published from this main sequence star, and then these people have worked really very hardly in getting away of all kind of biases. You can use that understanding and that kind of statistics to do this kind of predictions. And so this is what we have done in the paper. So you can then predict, you know, what is the fraction. What we haven't done is then, which is a folding of primary mass with what do we think is the folding of the companion masses. We don't have yet, while there is an understanding for the orbital separations, doing a folding with the companion masses is not yet justified. It should be done, but we still lack enough detail to do that in a way that I would think, okay, I can understand that, or I can believe that.
Yeah, it makes sense. Okay, unless there are any other questions, then I suggest on behalf of everyone, Leen, thank you very much again for a really great talk. I certainly learned a lot. I think a round of applause is always tough on Zoom, but were we in person, it would be much easier. But oh yeah, claps are going all around. So yeah, it was really good. So, as usual, we will sort of stay online for a little while to have some sort of informal social discussions. So